All right, guys, let's get started. This is 2.3, valid and invalid arguments. So in mathematics and logic, an argument is not a dispute. Like, it's not like the way we think of an argument between two people. It is simply a sequence of statements ending in a conclusion. Okay. Let's see, like, for example, here's an argument. If Socrates is a man, then Socrates is mortal. Socrates is a man, therefore Socrates is mortal. And you can interchange that with if P then Q, P therefore Q. Okay, so here's the definition, the big picture. So an argument is a sequence of statements, and an argument form is a sequence of statement forms. All statements in an argument and all statement forms in an argument form, except for the final one, are called premises, or hypotheses, or assumptions. The final statement or statement forms is called the conclusion. The symbol, the three dots that you're going to see me use it means therefore, by the way. And it's placed right before a conclusion. So right when you're about to say your conclusion or your final statement, you put the three dots. Now continue the definition here. To say that an argument form is valid means no matter what statements are substituted for the statement variables into its premises, it will if the resulting premises are all true, then the conclusion is also true. So to say that an argument is valid means that its form is valid. And we'll do an example in just a moment. So here are I'll upload this right after this, of course. So number one, identify the premises and conclusion of the argument form. So first thing you gotta do is read the statement, or rather the argument, and figure out what is the premise, what is the conclusion, and how many are there. And then construct the number two, you construct a truth table showing that the truth values of all the premises in your argument are true, and the conclusion. So you make a big table, see all the premises, if it's true or false, and then check the conclusion. So once you've done all that, number three is where you decide. So a row of the truth table where all premises are true is called a critical row. So you look at the row that has the actual statements you need, or your premises. Now, if those are all true in the premises, in the critical row, I should say, then the argument for form is valid. But if any argument is false in the critical row, right, then the form is invalid. Alrighty. And we'll do an example right now. Okay, so determine if the following argument is valid or invalid. So the first thing you got to do, so here's a question they give us. P implies Q or not R. And then Q implies P and R. Therefore, P implies R. So this is the two premises, and this is the conclusion. Okay. So this is the argument with its conclusion. So we have to go through one through three and figure out if this statement is valid, or sorry, this argument is valid. So we got to make a truth table, a big one. So P, Q, R, right? Yeah, should be good right there. Not R, we're going to need that as well. Q or not R. P and R. P implies Q or not R. Okay. Next one is Q implies see if I can make this a little smaller here. One moment. All right, so here's the truth table. So these are the premises, right here. So these are the premises, also known as assumptions or hypotheses. And those are these right here. Hypothesis, premises. And this right here is the conclusion. Okay. Make sure I'm on the camera there. So let's go through the combinations. So if they're all true, this should be false, right? True or false is true. True and true is true. Now we can answer these guys. P arrow Q Q or not R. So that would be true arrow true, which means it would have to be true. Right? Okay. Q arrow P and R, that would be true and true. So also true. P implies R would be true. Okay, so far it looks like maybe this argument is valid, but we have to make sure there is no case where you have true on the premises, and then a false on the conclusion. If that happens, then the whole thing is invalid. So that's what we're testing for. True, false. Not true, not false is true. True or true. True and false. There you go. P implies Q, so true implies true, that's still fine. True implies false, that's going to be false. P and R would be true implies false. Well, we don't have to check it anymore because remember we said if one of the premises are false, then it's not, that doesn't work. So let's keep going. True, false, true would make this false. False or false, it's false. P true and true. Okay, P, where's the Q? Yeah, P implies Q or not R. True implies false, that is false. Okay. False, if you start with the arrow false, right, for the Q, anything that comes after will be true. So technically, it would be true. But remember, we said that's nonsense in the last section. But since this is false, then who cares about the outcome? Okay, next one. True. False, false. Okay. So this would be true. This would be false or true. This would be true and false, right? Yeah. This would be true implies true, so that's true. True, actually false implies, if it starts with false, it's going to be true. Let's check. So now they're both true. So let's check if this is false or not. P implies R, that's false. So this is what we're looking for. So we have to go through every single combination to make sure this doesn't happen. If you have a premise, if you have all your premises to be true, but your conclusion is false, then that means that this argument is not valid. So you don't have to keep going anymore. You could. You'll find that there's other true truths that equal true, but it doesn't matter because if you find one of these, the statement is invalid. So this would be the critical row. Okay. I should say argument. All right. Let's go to another example. Well, actually, we need to define a couple of things here. Okay, let's go over the modus ponens and the modus tollens. So basically the modus ponens is it's probably the most famous syllogism, where a syllogism, I should probably define that first. So an argument form consisting of two premises and a conclusion is called a syllogism. So if it has two premises, like the last example, and a conclusion, then we call it a syllogism. The most famous syllogism is this guy, the modus ponens, which is just a Latin word for the method of affirming. So this is the most famous one because that's the one we use to prove mathematical statements. So pretty much a lot of the not definitions, a lot of the formulas, properties, and ideas in math are always written this way. If P then Q, and then we use P to prove Q. So it's kind of alluding to that, which is why it's called the, which it means in Latin, right? Method of affirming. Now, modus tollens. So here's the, by the way, here's the true table that I made before we move on. So true, true, true arrow true is true, right? And P and Q are true, true. So since both premises are true and the conclusion is true, this is my critical row. And none of them have that scenario where it's true, true, then false in my two premises. So we're good. So this is usually what we want to prove, that first one, when we actually start doing that kind of stuff. Modus tollens is also means the method of denying. So you're trying to deny something. So you start with two things that are false, and you try to show that your argument is valid. So this argument is valid, and so is this one. So you're basically denying. You're saying no, P did not happen, therefore P couldn't happen. Okay, and we can substitute actual arguments in there, which we'll do on actual examples. Okay, so we will most likely be doing modus ponens and modus tollens in the next example. Okay. Remember, two premises and a conclusion for both syllogisms. Okay, if there are more pigeons than there are pigeonholes, then at least two pigeons roost in the same hole. So this is my two premises and my conclusion, right? So if P then Q, that's the first premise, right? And let's see here. So if there are more pigeons than there are pigeonholes, so that's if P and Q, then at least two pigeons roost in the same hole. So this would be a modus ponens. So you have to identify, that's what the type of argument. So you would say at least two pigeons roost in the same hole. And this is by modus ponens. Modus ponens. Right, because we said if P then Q, P, right? So if there are more pigeons than there are pigeonholes, if P then Q, then at least two pigeon roosts in the same hole. So this implies, this is P right here. This is also P. Okay. So you have to identify which one is it. Okay. Now let's do part B. If 870,232 is divisible by 6, then it is divisible by 3. $232 is not divisible by 3. Okay, so this looks like modus tollens because we have, remember you have the way it looks, right? We said if P then Q and then not Q, therefore not P. So we have if P then Q and not P. All right, so identify the piece that it needs, right? So the answer here, since it's modus tollens, you would say 870 232 is not divisible by 3. This is because by modus tollens. $870,232. All right, let's move on to other. Well, I guess I should mention the modus tollens and the modus ponens are rules of inferences. So let me separate this guy here. Next example in just a moment. So rule of inference is a form of argument that is valid. Modus ponens and modus tollens are both rules of inference. The next example is more rules of inferences that are used in deductive reasoning. So generalization. So when you generalize a statement, so let's say the following arguments are valid. So P is true, therefore P or Q is true, right? That makes sense. Because if P is true, then no matter what you choose for any statements, P or Q, this will be true. Same thing that here, assuming this is valid, that means that valid implies that what this is true, the argument, the premise is true, the conclusion is true. So it doesn't matter what P is, it doesn't matter what Q is in this example, part A. Q doesn't matter, and here P doesn't matter. For example, if I said Anton is a senior. And then I said right after, Anton is a junior or senior. So that's still a true statement no matter what, right? Because I mentioned that Anton is a senior. Okay, I'm sorry, I was on the camera there. So Anton's a senior, so that's my P. This is P or Q. Okay, so that we're inferring that this is true for anything. Do some more examples. Okay, so as you can see, we have some common fallacies I want to go over. So fallacy is an error in reasoning that results in an invalid argument. So it happens every day, all the time. So using an ambiguous premise that's not really clear, using circular reasoning is another one. Jumping to conclusion, but the ones we're going to go over right now are the converse error and the inverse error. Okay, so the converse error, this is an example here. So if Zeke is a cheater, then Zeke sits in the back row. Zeke sits in the back row, therefore Zeke is a cheater. Clearly, then it's not true, right? That doesn't really make sense. So that's considered to be a converse error. Now, an example of a inverse error. So if these two vertices are adjacent, then they do not have the same color. These two vertices are not adjacent. These two vertices have the same color. So that's not necessarily true. I mean, it really depends what we're talking about. So since it's not clear, this is considered to be an inverse error. So please read the definitions a little bit more on inverse and converse, but that's pretty much it for 2.3. Do not think I am going to talk about anything else. So the homework will be one through 23 odd and 25 through 33 odd.